168, yeah.
So was that the one where you were like, love networking? Or...
That was the one where I was like, I found the most beauty in it, I think. Like, I also liked TAing the ML class, but I found this beauty in like systems thinking of abstractions and like how you layer things and how you organize a larger system and extracting kind of design principles. Yeah, it's kind of funny. I was good at that. My brain works that way. In contrast to, if I think back to like taking CS70, which at Berkeley is like probability and discrete mathematics and stuff, I was not good at that stuff. Like, I was nowhere near the smartest at that stuff. I was nowhere near the best coder. I was a decent coder. ML stuff, I took that and I could do it, but I just hated it.
Yeah.
Hated doing it. But then like systems thinking, my mind just like loved understanding those layers. And so I found like myself the happiest when I was thinking that way. And so at Berkeley, it was actually not just TAing 168 that pushed me towards that. It was taking operating systems, security, and compilers. Didn't love compilers, loved security, and I quite liked operating systems, and then loved the layering and networking. And then that's eventually what like led me to realizing I was a systems person. Yeah.
Welcome to the Thinking About Computers podcast, where we talk about thinking about computers. Our guest today, Alex Krentsel, a second-year PhD student at UC Berkeley and part-time research engineer at Google. Also a former bell tower musician for the Berkeley Bell Tower. Welcome to the pod.
Thanks for having me.
Alex is a computer networking researcher, the first we've had on the podcast. Also a former full-time Google engineer and a former UC Berkeley undergrad.
Yep.
So I, also a former UC Berkeley undergrad, how was your undergrad experience? I feel like, did you do CS?
Yeah, so I was an EECS major, and I also did a music degree.
Dang.
Randomly, I know. And I always get asked, like, oh, did I like combine them, or like, do you want to work in like generating music? And like, no, for me it was totally separate. It was like, I wanted to do my like CS homework and then take a break and do like practicing violin, and that's how it was the whole time. It was an interesting experience. I came out of state, so I finished high school in Kentucky, and then coming over to California was a big like culture shock. I hadn't even visited the West Coast before. Berkeley's like what I think like 70% in-state, something like that.
Yeah.
So out of state is smaller and smaller, and so I found it tricky to find a community of people that were like. Everyone knew each other. All of the California kids knew each other, and so coming in as out of state was really tricky. International kids stuck together.
Yeah.
And they had stuff they could relate on. In-state kids all knew each other. There was like I think 3 other Kentucky kids. So I was one of 4 coming from Kentucky, and so we knew each other. But otherwise, that adjustment was tricky. But I actually really liked the big like public school vibes. It's a trade-off. I hear people talk about, oh, it's so tough at Berkeley. You're one in a sea of like 1,500 kids in your intro CS class. I thrived in the like largeness of there's all these different interactions, and I think I was comfortable like kind of going to get help when I needed it. But I know it can also be really tough if you need help and you don't know where to go. So I liked it, but I also recognized there were drawbacks. Yeah.
I also went to a big state school.
Yeah.
As did Lisa. So
well, yeah.
Not a lot of contrasting experiences.
Yeah, I mean, definitely agree on the like. I didn't have a problem asking for help class-wise, and I think, well, the CS program at Berkeley is very large, and many classes, like the TA to student ratio is like not ideal.
Yeah.
They like do provide quite a lot of resources. Berkeley in general, I think, provides a lot of resources. They just don't tell you that
exactly.
they have them.
Yeah.
So like they have a ton of office hours, like they have a lot of like homework parties and like support things, but then like oftentimes people just don't really go to them, or they go to one and it's like way too crowded.
Yeah.
No.
Yeah. I do have to say though, on whole, like I really appreciated how real Berkeley felt, especially compared to like talking to friends who went to private schools. I think just like one, just like the physical environment, like there are all sorts of people on campus. We're in kind of a more urban setting. Parts of being off campus can feel unsafe sometimes, and there are all these drawbacks, but I really liked just how real that felt. And also classes felt like you also, I don't know, I came out like learning how to advocate for myself and I do love the quality of the education that I got. Like coming out, all me and kind of my Berkeley cohort, when I came to Google, seeing like just we got a really great education. Like the CS classes are fantastic. So I'm really happy with Berkeley.
And am I right that you taught a bit at Berkeley?
Yeah, I TA'd at Berkeley. I TA'd 5 semesters. It was like the main thing that I
a lot
loved
at
to
Berkeley.
do. Yeah. And I tried a bunch of different classes. So my view on TAing was like, this is a great way to learn the material more in depth, because going to explain the material you have to see it from all these different angles, because you don't know what angle is going to resonate with your students. And your goal is to kind of present snapshots from different angles that are like 2-dimensional, that let students reconstruct it in the higher dimensional world that you occupy in that space. And so I TA'd E16A, which was the intro to electrical engineering class. So that was linear algebra and circuits. Then I decided to try 61B, which was a data structures class. Then I tried 168, which is our networking class. And then I TA'd 189, which was our ML class. And just very different classes, which forced me to like really deeply understand different areas. And it helped me figure out eventually what my like research interests were actually.
How did you realize you were an ML person? Did you go through a similar journey?
Well, I actually never took an ML class at Berkeley. I guess I took 188, which is like a fake ML class. Yeah, like an ML class where you just learn like a Bayes net. You don't really learn anything. I really loved the systems class actually. 162.
Yeah.
I like 61C, but I was pretty not great at 61C. I wasn't super great at 162 either, but like kind of the similar, like the beauty in people who've thought of these abstractions that are like so simple when you look at them, but then they just like fit so nicely together. I really enjoyed. Did not care to calculate cache hit rates.
Yes,
that was not my favorite part of that course. But like I loved the projects, and just like David Kohler taught it.
Oh,
just
that's
like
great.
I would go to his office hours every week and no one else went, and just hearing him wax poetic about operating systems was like a pretty amazing experience.
Speak beautifully. He's my manager at Google.
Oh, really?
Yeah.
Does he still wax poetic about operating systems to you?
He does, about whatever topic we're talking about. Speaks beautifully.
Yeah, like the way he talks is also just very like, I'm entranced. But yeah, so I guess my education didn't really lead. I guess I really liked linear algebra, but similar to like your math or your CS and music, I majored in CS and math, and like these things actually definitely should be like related, but I viewed them as completely separate. Like I did not really find linear algebra that useful for any of my CS stuff, aside from like maybe like 61B, but in general,
structures,
I found them pretty separate to one another. Sadly, I didn't do any TAing in undergrad though.
Really?
Yeah.
Okay.
It was.
Did you want to get an interest, or you were just too busy?
I had an interest. I definitely wanted to when I went in, but I started research pretty early, like beginning of my sophomore year, and then by the end of my sophomore year, I was doing like basically research full time, and decided I liked that a bit more than teaching. Because it seemed like teaching was like you kind of really had to climb a ladder for teaching. Which I just I guess I didn't want it that much.
So this is good context. Maybe I'll share at Berkeley what they have. Berkeley classes are huge, right? Especially the intro classes, and so we have a bit of a pyramid structure when it comes to our TAing system. You have a 1,500 person class taught by a single professor, right? And then you have like an army of like 30 or 40 TAs that are then like run discussion sessions. So those positions are great. That's probably what you want it to be. That's what I really.
Those are like the
coveted spots. And at Berkeley, they pay well. They come with some tuition remission, so that everyone wants them. But then below that, there's a tier of people that are tutors who are paid less, and there's maybe 100 of them or something, and they're like helping on office hours. Below that are readers, and there's maybe also about a lot of them. They grade assignments, and then below that there are clubs, CSM, computer science mentors, and a few other clubs that get you some teaching experience. And so you start off, the path for these lower division classes is you start off in one of these clubs, you do that semester, you step up a level in the club, you become a tutor or reader the next semester, and then you become a TA. And so you have to kind of work your way up.
Yeah,
So-
I did the first level,
Yeah.
and then I was like, no, I'm not doing this. And then I was a reader for some math classes, but that was like much more chill.
Yeah.
A bit different at UMass. I TA'd like every semester pretty much,
Uh-huh.
and I was the only TA for any of the classes that I TA'd. Just me. I would have office hours. No one would show up to them almost ever.
Mhm.
Yeah, that was it. There was no readers. There was no graders. Just me and the professor.
What did you do? You run discussion sessions of some sort or recitation sections? What did it mean to be a TA?
Yeah, for some of them you're on a discussion. For some of them you're the grader and like office hours and stuff.
Yeah, okay.
Um,
So you do like whatever your professor needs you to.
yeah,
You did
like
your
proctor
part.
exams. But this was also in 2012, 2013. So
Yeah.
I think CS was just smaller back then as well. Like,
Yeah.
um,
I think Berkeley has definitely pioneered over the last 10 years what it means to scale
Yeah.
computer science education.
Yeah.
Going all the way up to, I think at its peak, 61A, our intro CS class was, I think, 2,400 students at its
Yeah.
peak. That's how high it got, which is crazy to have a single professor running a class that big.
I think, isn't Data 100 or like Data 8?
Is that the biggest now?
Yeah, I think it's one of those two.
Yeah,
is now the
okay,
biggest.
probably.
But I mean, they're all at ridiculous numbers. I'm
Yes.
sure they're
Yeah.
equally as. Yeah, it was definitely a weird switch of like, this probably happened before I started, but I took 61A over the summer, so it was 400 kids,
Yeah,
which
yeah.
was like pretty fine.
Yeah.
But I think it was like my sophomore year or something that maybe it was my freshman year where there were some classes where they were like, hey, if you don't want to go to class, don't come because we can't hold everyone in this class.
Yeah, I got told that too. Yeah.
And I was like, well, I guess I will hope that people don't come because I want to come. And it turns out that, yeah, that's actually a totally fine plan. Most people don't care to
most
come.
people don't. Yeah.
So what are your hot takes on teaching, if any?
Hot takes on teaching. Well, this is interesting. I think the thing I get pushback on what I say the most, I think, is like, maybe this isn't that hot of a take, but people argue with me on this. I think different TAs are good at teaching different kind of types of students.
Mhm.
And actually, this is something I really like at Berkeley. At Berkeley, the system is there's a bunch of discussion sections, and students kind of self-select what sections to go to. So you're assigned one, but you don't have to go to that one. And I think I found that, like, I don't know, I have some friends that are really good at some teaching friends that are really good at taking students that have never thought about CS before, like this idea of computational thinking and how you think about maybe the ideas of thinking about recursion or something for the first time, like, or how you think about like statements being evaluated and just the really core ideas of computational thinking.
Mm-hmm.
Some people are really good at being able to kind of get students from nothing to like 0 to 1 kind of in that space.
Yeah.
And I think other instructors are really good at taking students kind of from there to a different stage or building on concepts in the middle. And there are other instructors that are really good at teaching like much more advanced concepts and pulling together ideas from different classes. And so maybe one of my hot takes and one of the things I've learned through teaching is that I'm good at like somewhere towards the higher end of that, of pulling together a bunch of different ideas. And I'm like much less good at like getting students from kind of the state of not having thought about computers to like having some notion of computational thinking. I found that out the hard way. I like spent a semester lecturing Intro to CS. This was after graduating. I went for a semester. I taught at Howard, like their equivalent of 61A. I was the lecturer. It was like so hard to do that. I tried my best. I'm okay at it. But then there are other people I see teaching that are just like really good at that kind of thinking. And so as I think about what kind of teaching I want to do in the future, I kind of think about that. Of where can I do that particular slice of teaching? I don't know if that's a hot take, but people have argued with me whether that's right or wrong, or to like, you should be able to do all of it. I just find myself being good at some parts of it and not others.
Mm-hmm.
So you also did Addis coders, right?
Yeah.
Teaching like high school aged kids. That's also like an introduction to computer science sort of thing?
That one was interesting. So that was this last summer. A professor at Berkeley, Jelani Nelson, runs this program called Addis Coder, where he takes the top 100 or so high school students in 11th grade in Ethiopia. Which, by the way, fun fact, can you guess the population of Ethiopia?
I'm gonna try to get a number out there.
Yeah.
It's like between $1 million and $1 billion.
Somewhere between $1 million and $1 billion, probably.
Okay, is it... Oh, I'm really bad at this. Is it like... I'm gonna say somewhere between 5 and 10 million.
5 and 10 million. Okay. And do you have a tighter bound?
Take the over.
I'll take the over. Yeah, okay.
10.
I think it's 115 million.
Nice.
Wow.
So, right.
Very wrong.
Lots of students. And so the reason I say this is because now imagine out of 115 million students, you take, or it's just people, I don't know, some slice of that, some tens of millions are students, and you take the top 100 or so. They were super sharp, like really, really, really sharp students.
Mhm.
I really enjoyed that teaching, actually. They were really good at math. So the program was, you go, Jelani has this application process, takes the top 100 or so students based on their scores on the national exams and some other criteria. They're brought to Addis Ababa, the capital of Ethiopia, and housed, and they 8 hours of class a day for 4 weeks.
Mhm.
So 5 hours of lab and 3 hours of lecture every single day. And these students come in with really good math, but absolutely no coding experience. And so that was really new to me. At Berkeley, I taught students that kind of had some coding experience, some math. There were some, super strong kids. Here, this was super, super strong at math thinking, zero experience with programming.
Yeah.
And so, I was there for a week, and I kind of taught them the second week where we talked about recursion. We talked about how to draw images. So just learning arrays and little simple problems of, here's an image, apply a filter to this image. Very different teaching experience. As I was saying, I'm okay at teaching, kind of getting people from 0 to 1, but here it was really better for me because I could try to map computational thinking back to math concepts.
Yeah.
And so the students picked that up really well. I was super impressed. But yeah, really fun program. It's happening again this summer. Anyone can volunteer to be a TA, by the way, or a lecturer. And so I think it's addiscoder.com. You can apply. Yeah.
You just started one in Jamaica as well, right?
Jam Coders. That's been going on for a few years too. And that same exact program. Really, really cool. The goal is also these students kind of come out and then they have someone to write letters of rec for them, and they apply to schools in the US or in Europe or wherever they want to go.
Yeah. Very cool.
Mm-hmm.
Was it what was your sense of what kinds of things made sense to teach to students with that background, introducing them to computer science?
Well, I found that they picked up ideas around variables and functions pretty quick. Functions mapped pretty naturally to some notion of equations.
Yeah.
I also was again super impressed at how quickly they picked up recursion. This was week 2 of them learning CS.
Yeah, that's pretty impressive.
Super impressive. For example, in comparison, the class I taught at Howard, I think we got to recursion at week 11 in the class or week 12. Again, it was much less. I mean, we weren't studying. It wasn't 3 hours of lecture, 5 hours of lab. Yeah, but still, it was. I think the notion of something being self-referential and kind of how neatly base cases this is kind of nice, beautiful circularity to recursion, and how a base case kind of is the thing tucking its tail back into itself. It's really cute. They pick that up so quickly. In general, just thinking about how I can map things back to math. I think that's how I thought about the curriculum a lot. The other thing, though, is the thing that's universally true is when people are starting to learn CS, the more visual and tangible you can make it, the better, generally. And so I found the students really loved, rather than just trying assignments with array accesses and for loops, mapping it to filters on an image, Instagram filters, that really clicked with people. And so just seeing real world applications, that works well, I think, across the board, whether you're teaching, top 100 kids in the country or whatever, large course at a university.
Yeah. The topic that comes up a lot in my research is a question of so in databases, a lot of people are focused on declarative interfaces to code, right? SQL, data log, things of that nature, where you write kind of logical expressions, you kind of state at a high level what you want to have happen, and the computer, the details are going to be worked out for you by an optimizer. In PL land, it's kind of all functional programming, which is also kind of high level, but it's a different paradigm. And I feel a common knock against both of these is that no one wants to do functional or declarative programming. People want to do imperative programming, right? And there's like is that the more natural way to think about coding, or is that just how people learn to code? And like most people don't get exposed to functional programming maybe ever, maybe when like they've already been coding for 10 years. It's like already kind of burned in their brains how to do it in an imperative way.
Yeah.
Working with people who are first learning to code, what's your kind of impression of that landscape?
Ooh, that's a great question. I've never thought about that. Well, I think I think that I find that the students, again, I'll tie it back to kind of real world applications. The students pick things up in a way that is most applicable to the real world. And I think I'm just trying to think back to our intro CS class at Berkeley. I don't know if you remember that part of it is taught in, like, they teach scheme. Yeah. And that's like a notorious pain, and everyone struggles with it. I'm trying to think if that's like fundamental for just like, okay, do people think more like I think it actually just ends up being more about like what feels most applicable to things they can actually build and things they can actually go like apply. At least I feel like when I think about the students that are kind of most successful or most excited, they come back to me after class and they show me something that they've built. And so maybe that's why I think students do better with learning something like Python or something like JavaScript. It's just because it's more applicable to the real world. Like, I wonder what the world would look like if you could build more stuff with Scheme, for example.
Yeah.
I've never thought about like what is more just, is there a world in which, I don't know, everything is taught in Scheme and students build everything in Scheme and that's kind of the way they think? I don't know. That's a great question.
Yeah. And I know more CS like college curriculums teach functional programming as like an intro course in some way. My undergraduate curriculum didn't involve functional programming. I think it was all like object oriented Java stuff. But I know like Harvard and MIT do like OCaml and Scheme and whatever.
So where was your exposure? Like, how did you learn? Was it for research or was there?
Yeah, like working with PL researchers. Like, they're very hyped about functional programming. I don't know. For people with like I imagine for students coming in with a strong math background but no CS background, like maybe that's one of the optimal audiences for like a more functional perspective on computing.
That's interesting.
But, and same for declarative, like logic-based languages, like Datalog, like stating things as logical rules. Like, I don't know. I find that like somewhat natural for, at least for like kind of algorithmic problems. Not for building like a website. But it seems like a lot of people don't really like that kind of interface to expressing their program logic.
Do you see a lot of functional programming in industry?
No, not really.
No, it's all object oriented.
Yeah, I mean, I think my experience has been what did I do? I graduated and I worked at YouTube for a year and a half, for 2 years. I worked on the pop-ups on YouTube. You've ever seen the like try 1 month free of YouTube Premium pop-ups? Yeah, that I built that.
Wow, so incredible!
Huge impact. YouTube Premium subscriber?
Yeah. Oh yeah.
You are?
I am. So
you are great. Right, I'm sitting with 2. Yeah.
It worked.
It's incredible. Those things are shown like literally billions of times a day.
Yeah.
So you would think, okay, there's like one person. I say I built those just to simplify it. There's like a team of like 20 of us that work on those, on all aspects of serving them and targeting them and optimizing them. Which offer do you show to who? But like all of that was all in C++ backend. And then, in research land, also everything there we built was in Go, interestingly enough, in networking at Google. So no, I didn't really think about much functional programming, but I'm sure there are many teams inside of Google that do. My teams didn't.
Yeah. Yeah, when I was at Microsoft, everything was C++.
Yeah.
So you're still at Google part-time. how have you noticed, like, you do research at Google? Or?
Yeah, so I'm in the systems research group. It's
Mhm.
run by David and Hank Levy.
Oh, right, yes.
Yeah.
The legends.
The legends.
How have you, like, is it two completely different worlds, academic research and research at Google? Or, like, do you think what are the similarities, differences, focuses?
I think there's actually three categories that are interesting to compare. So I'll add one more. So there's research in academia at Berkeley. There is, and I'll narrow this down to systems research. I think the answer from ML might be different.
Sure.
Like, then there's research inside of Google, and then there's the like infrastructure teams at Google. That comparison is also pretty interesting. So it's kind of this continuum, the sliding. I almost see it as a bit of a sliding scale where the infrastructure teams work on like what are the immediate infrastructure problems that we need kind of solved. And so we're running into this problem with our network. How do we like deal with the fact that, I don't know, some protocol isn't scaling well as the network continues to grow and double in size every X years or whatever. I find the research team really focused on thinking about what are the problems we're going to see in the next 10 years at Google, and why they're really well positioned is they research at Google has access to kind of all the data of what's happening in the systems at Google.
Right.
And what's interesting about data isn't just like a snapshot today. There's cool stuff there too. That kind of data is like, okay, I have access to all these images or something, and can I train a classifier on there? Whatever the
Right.
ML people do. I don't know what you guys do. But the interesting thing for systems researchers is trends. That's like a lot of figuring out, a lot of a really successful research project, beyond just a single project, but like a research vision is saying, look at the way the cost for memory is going versus the way that cost for compute is going. And look at how these curves diverge. We need something to solve this problem in the future. And again, that's where systems research has a really interesting position, where you're sitting inside of a company that has all this data on like how its resources are being used, and you can kind of see and extrapolate where we're headed. And that's where I see the system research group's strength is like you can picking those problems that are going to be must solve critical problems for the company in 10 years,
Right.
and kind of researching in that direction and trying to figure out what problems we're going to run into, this kind of expedition model. That's how I see kind of the research that happens at Google. And I'll compare that to academic research, kind of what I see in Sky and what I see in NetSys is you're kind of off wandering a little bit blindly, it feels at times. And it can be really frustrating because you're like, the further I'm 2 years into my PhD now, the further I get, the more I see kind of ties between doing a startup, and then when I hear startup friends talking about kind of finding product market fit, kind of wandering around, and how I see researchers looking for projects and finding impact. You're kind of wandering around and looking for what is going to be needed. But I guess there's also a flavor of just like, what are you excited about, and the freedom that comes with being an academic. But I think that also lets you then wander beyond the parameters of at Google in the research group. You're working on cool problems, but it has to tie back to kind of where the company is headed. And so you can even predict like, okay, you can see where Google is putting a lot of its energy, ML stuff. Of course, the systems people are now like, hey, how do we support ML training is going to go crazy. ML serving is going to go crazy. And so those problems are high priority. And so you get to look at trends where those things are headed and what are the problems we can solve. But they're not really guardrails, but they're just kind of guiding rails of the types of problems you work within. And I feel like in academia, you can kind of wander in all these different directions and hopefully try to figure out trends based on a public view of the world. So I think it's harder. In industry research, I find that you can kind of really motivate your research by looking at what the company is going to need. I find on the Berkeley side, the research I do, it can be harder to kind of motivate my research because I don't have access to this direct data, and I feel more lost sometimes trying to prove myself.
Yeah.
But I have this freedom to go in many different directions and it almost seems like this part I haven't figured out yet. Maybe ask me in 3 years and maybe I'll have a better answer for you. But it seems like almost magic that you can maybe stumble in a direction that ends up being really impactful because that's where the industry heads.
Yeah.
I'd be really curious to hear someone who's kind of a successful senior PhD student who's done this explain how it is that they figured out that this is where the field is headed. Mm-hmm. That's something I haven't answered for myself yet, but yeah.
Yeah, that's a big challenge, I think, of academic research. It's something, I found very difficult.
Have you figured it out?
No. So, I mean, like in industry, when I was in industry, it's very clear what the problems are, right?
Yeah,
Like they're right
yeah.
in front of you. You
Yeah.
can really quantify them. You can say like, this is how good it would be to solve this problem, and this is how good it would be to solve this problem. So I should solve this problem. Like this is twice as good of a problem to solve.
Yeah.
And like in academia, it's very hard to get really compelling problems that need to be solved, and that it requires academic novelty to solve them.
And talking with other people in my cohort, second year PhDs, we were first year's PhDs, the thing keeping people up at night, like young PhDs, of which I count myself, is like, does anyone care about my problem? It's interesting, which never happens, I think, in my experience on the industry side, because like you can motivate pretty clearly, and like to work on the project, you have to make a case to someone of like why this needs resources. And so, yeah, just an interesting trade-off I see. What have you felt?
I mean, I think it's a bit of the same. I think it's a little different in ML in that I think you get a lot more positive feedback, just because it's a pretty hot area.
Yeah.
And it depends on the person, like the research direction. I think a lot of people, and definitely early in my PhD, were working on problems where I was like, do we really need to solve this? Like, probably not. Like, this is probably not that useful. Like, I don't expect anyone to use this. This is more of like a cool academic thing, which is fine, but can definitely lead to more like staying up at night.
Yeah.
I think one difference probably with ML is that like the research I work on now, and a lot of people that I know in ML like actually use the things that they do, that they build, and like because people interact with like ChatGPT or like vision models like on like almost a daily basis, like you kind of already have like that immediate use case, because you're already interacting with the product so much. I think much more of what keeps me up at night is like, I am not as worried that no one cares about my problem. I'm more worried that 20 other people are currently working on this problem. And so people care about the problem, but they're not going to care about my solution.
Yeah, interesting.
But I mean, I prefer that to the other existential crisis. So
yeah.
But it is kind of I agree that it is kind of amazing that some researchers can just stumble upon like some problem that actually ends up being like supremely valuable in industry. Like this has happened in ML quite a bit in the past few years, which has, I guess, been counterintuitive to me. It's like, oh, all the like industry has all like the big resources and they have all the data, which is kind of king in ML.
Yeah.
But a lot of like the core architectures that people use now were like developed in academia, which I still find, I guess I find quite encouraging. Yeah.
Do you find that holding as model sizes increase? So it seems difficult without compute resources to even try out architectures.
Yeah.
Like the transformer architecture, right? That came out of Google.
Yeah, right.
Yeah.
So I think it's a bit of a trade-off. And I think there's a shift. I think there's a fair amount of work, for instance, like in vision and language. There's been a fair amount of work in like, how do you build an architecture to like combine vision models and language models? And there's been a couple of papers that have shown like you can build these prototypes on kind of a small scale that end up working at a larger scale. So I think from like the architecture building side, people have been able to continue doing this in academia because the things that they do just scale well. Do you get something that's like super, everyone's going to use? Probably not. But yeah, there's definitely been more of a shift to like, we're going to use stuff that companies have already built, like the assumption that someone else will train this and I will do some like fine tuning, or I will just like use this for a different application. But there's definitely still a lot of people who develop successfully models that companies then take the GitHub for and add 20x more compute.
Yeah.
3,000x more compute. Yeah. So pretty good. So I heard you did a bit of ML research back in the day.
Yeah.
A little bit.
Yeah. I don't know if I can
What are your
relive those.
thoughts?
This is a fun experience. I took, oh my gosh, what was it? CS 198, 126. I forget the number, but it was computational photography with Alyosha Efros.
Yes.
Okay, fascinating professor.
Love Alyosha.
Yeah, I really like him too. There's like it's a great irony here. He's, I think, either fully or partially, certainly legally blind in one eye.
Yes.
I always found that fun, like ironic or funny of him teaching the computational photography class. I remember he would stand in the front and kind of like one side of the room would like he would have to like intentionally like scan the room with the one eye because he would miss questions in one side of the room.
Yeah.
Fantastic teacher. Got me really excited and I wanted to do research with him. And so I went to him and I, what problems do you have? And I started working on this project that was, at the time, the project was for a given video clip and a pool of audio clips. I want a model that'll pick the best audio clip to go with the video clip.
Mhm.
That was the problem. Yeah. Not even generate audio, not any of that. This is just, here's a pool of a bunch of snippets. Let's try to map it. And a previous undergrad had worked with a grad student for like a year and a half on this project and could not crack it. And I went and I took over that project from the undergrad who was graduating, Phil Kuznetsov, who's now like went off and working at startups. I was just lost in the whole black box aspect of ML. Like, no one understood why certain things worked and why they didn't.
Yeah.
And that was really frustrating to me. In hindsight, great evidence that I'm a systems person because like now I'm all about extracting principles and like defining these systems and layers in ways that they can interact, that are predictable and make sense and require structure. I was not interested in this like hyperparameter tuning, which is what it felt like at the time. And now
that's what a lot of it is.
Beyond that, now it seems like it's like all these different architectures that people are trying where they have ideas about why they want to try it this way, but it's not from first principles derived. It's kind of like, I don't know, they're like, oh, this is why we structure these layers and why we do these certain things, and this is why it might work, but we don't actually know.
Right.
Could not solve the problem, really struggled with it. And in the end, like, didn't get very far, kind of wrote up a draft for a blog post, but kind of didn't get results that I wanted.
Yeah.
But learned a lot about myself in the process of what I liked and what I didn't like. As I'm saying, like, this black box nature, not for me.
Yeah, no, I think it's something that a lot of people struggle with. It's certainly something that I am not a fan of. But I came in doing interpretability, so it's kind of, I guess it was well poised of the whole crux of that is that we hate black boxes. And then as you go through interpretability, at some point you realize that you will never learn this black box. It is actually a black box, and you can find some cool like pattern. You can understand some general ways that these things work and some common patterns that it learns and how it composes these patterns into like more complicated like reasoning. But you're never going to have like a nice, like one of the big things that people have been very interested in is this idea of like a semantic neuron or like a polysemantic neuron. So like, can I find parts of the network that are really in charge of like for classification, like this is in charge of like detecting eyes, or for natural language, like this detects parts of speech. And it's always, the results are always fuzzy. It's always like, you can find something that like mostly looks at this, but it's never fully in isolation. Like there's a lot of fuzziness that's going on.
Yeah.
And you really kind of got to embrace the fuzziness, which I think for a lot of people is hard.
It's frustrating. It's frustrating for me because it's like, you're trying to combine that fuzziness with science, and science is generally pretty like rigorous and maybe doesn't handle fuzziness quite as well, or at least computer science.
But I think that's like the beauty of it, because then you need to figure out a way of like, how do I measure this? Like it is so fuzzy. But I need to figure out like, how do I actually prove that this is true? Like I agree, I'm not a huge fan of this. Like I think there is the utility, and we tried these 1,000 things, and this is the one that worked. But it's just not very satisfying. Like trying to figure out like, this is my hypothesis, and like because I can't actually look at the internals of this model, Like, I need to come up with a bunch of clever tests that can convince me and you that, like, this is what is happening.
Yeah.
Which I think is like a quite interesting exercise. And I think, like, after going back to like, oh, I want to maximize accuracy, it's like very unsatisfying after. It's like, I already know what the goal is, and like, I know I can tune a ton of hyperparameters and probably get there.
Yeah. Do you run into fuzziness in PL and DB land?
Yeah.
I definitely also have this intuition of like finding it very unsatisfactory when there's like a black box and you don't really know why it's doing what it's doing. I often try and solve that problem by like proving some mathematical results about like why things are working how they're working. But I guess one place where that often isn't a satisfactory answer is that like you can't really model the full performance behavior of like real systems in a accurate enough way.
That's true.
So like you have a clean model on a whiteboard that like is satisfying and like things make sense, but then like your experiments won't exactly match that. So that's one source of black boxedness.
Oh, that's super true. I've been running into that in some of my research now. Recently, I've been looking at applying formal verification to networking. So the idea is, for anyone not familiar, you can try to take and encode some model of your system about how it behaves. And if you can encode that in some sort of formal logic, you can explore all possible kind of encodings or all possible input values to your system and provide some guarantee about how it behaves. And then you have all these academic results with this model showing that, okay, your system is guaranteed to behave a certain way, but then in reality, the model is way more complex. And it's those aspects that you've abstracted away that actually break some of your kind of guarantees. I think it's kind of a unique aspect of we're so, as systems people, closely positioned to industry, into real world huge systems that that complexity, the only way to kind of prove anything is to abstract some of that complexity away, but that also makes your results less applicable in some way. Yeah.
Is this what you worked on for your Sigma paper, which just got accepted? Or
for SigCom? Yeah.
SigCom, sorry.
No, this is a follow-on project. The SigCom paper was on decentralizing software-defined networking. So for some brief context on that, networks usually, how do they work? For the longest time, they worked by each individual router would have to make decisions. When I see a packet that's headed to this destination, I'm going to put it on this link. And you kind of rely on the fact that all the routers have kind of make decisions that get the packet to its final destination. Then there was a big movement 15 years ago to take that decision making off of the routers and centralize it somewhere. And so have one computer that finds out what's going on in all parts of the network, compute paths through the network, and tell every single router how to forward traffic. And that sounds great. It works really well. You can now optimize because you have centralized decision making, but you have this problem where what happens if that router goes down, or that computer goes down, or what happens if some information doesn't make it to that computer? And so our paper was about how we can take this kind of centralized decision making, but decentralize it again in such a way that you don't have a single point of failure, because that's the network is the plumbing for all these other computer systems. Every computers have to talk to each other to get things to scale. And so it's how you decentralize your control plane. Again, very clicked for me because it's all about layers. It's all about organizing kind of the structure of your design in a way that allows you to do more and allows you to reason about how your system's going to behave. And that'll be appearing this in SigCom in 2 months. It'll be great.
Oh, exciting.
Yeah.
So networking as a field, how would you kind of describe the field of academic networking research? What are the big problems? What are people working on? What's their kind of typical context and background?
Yeah, that's a good question. And I think now I'm finally well positioned to answer it. It's funny, I was not well positioned to answer this when I came into grad school. I just kind of tried a sliver of networking research in industry. I loved it. But now the past 2 years, I've been spending time in have a better sense of the field. There's a couple of kind of big directions. Well, there's a bunch of directions, so I can't even summarize the entire field for sure. But one area that people have continuously worked on is called congestion control. I don't know if you guys are familiar with congestion control.
I mean, I've heard of it.
This fun problem where there's limited resources on the internet, and the internet actually works. There's two structures of how people can communicate. There's the phone system, where it's circuit switching. Circuit switching is where you like dedicate, I don't know, Connor and I want to talk across the country, and we're going to dedicate resources on each cable along the way. First, set up a circuit, and then we can talk. We need, I don't know, this amount of capacity on each of the cables along the way to carry our image back and forth. That works, but it requires a bunch of resources because we have to reserve the maximum of what we're going to use the entire call. And so if we turn our camera off or something, we start using much less, but we still have to reserve the entire size. And so the dominant way that networks work is actually packet switching. Instead, you have best effort delivery. And what that means is every person trying to talk breaks their kind of transmissions into little pieces, and they try to send them through. And when there's enough capacity, you can send more. When there's less capacity, you slow down and send less. And the mechanism by which you dictate how fast or slow each person sends is called congestion control. That's how we manage kind of signaling back to senders to slow down in a way that's fair so that no one can game the system, no one can just start sending a ton. Amazingly, that problem has been around since 1986 when the TCP, even maybe it was further even back, the original congestion control problem was formulated and solved, or attempted to be solved. As different environments come up in data centers, in satellite networking, in just wide area networks in general that crisscross under the ocean, how we do that congestion control, that problem just keeps on giving. So that's a big thrust. People in our lab, Sarah McClure works on that problem, as Scott and Sylvia, my advisors, do as well. I see people working on different aspects of data center networking. And so in a data center, especially now with ML, you have all these compute clusters and they need to talk to each other, and data needs to move back and forth and weights need to move back and forth, and gradients and updates. How do you provision a network that has any computer can talk to any other computer at their maximum rate? That's actually a really hard problem, especially as you get thousands of computers that all need to be able to talk to each other in a way that minimizes cost. That's, by the way, one of the fun things is a lot of networking problems I feel like can actually be solved by throwing money at them.
Yeah.
And so a lot of what we're doing is how do we solve this problem with the constraint of minimizing resource usage, which are kind of duals of each other. The dual of that problem is you have a network, how do you maximize the things you can do with that network? Yeah. There's a whole formal verification land where people are trying to apply, as I talked about, formal methods to reasoning about your networks. I mentioned kind of space networking. Yeah, I don't know. Those are the parts of the field that I see. I'm sure there's plenty more that I'm not representing well.
Is there any one that's like in vogue right now? Very popular?
I feel like everyone's talking about applying machine learning to like whatever their field.
Of course.
Yeah, there was like
Can't escape.
so many papers on like, okay, what if you apply machine learning to like solve your paths through the network routing, which is a problem that I worked on for a while. There's people like trying to generate configuration for routers. Tell your ML model, I want to generate a configuration for a router that does X, Y, Z, and have the configs stat out. Yeah. One important area I missed that I didn't mention, which is my advisor Scott's principal area, is like core internet scale architecture. And it's like, how do we see the internet evolving over the next 10 years? And how do we enable innovation in an internet that's becoming increasingly siloed? Like today, Microsoft, Meta, Google have these huge networks that crisscross the world, and they are innovating. They're putting caches into the network at the edge. They're putting compute into the edge. The public internet was not designed to kind of evolve so much functionality, build new functionality in, because whatever you want the internet to do, you have to get everyone in the world to kind of agree to support that. And that's really tough. And so this like future of the internet kind of scale architectural thinking, not many people do that, but I really appreciate those kinds of projects. Yeah.
Is it like feasible to kind of make headway on those sorts of things? Like, is there a path to adoption? Like you said, like it's kind of a lowest common denominator
Yeah,
adoption.
It ends up being a lot of creative thinking of exactly that, lowest common denominator. What can we do with using the lowest common denominator in creative ways? And so, yeah, like Scott and Lloyd and Emily, a few grad students in my group, have been thinking about that. And yeah, they have a proposed way to do this, the minimal kind of asks. The other fun thing about it, networking, is you have to reason about how like federated entities interact with each other, not just technically, but also monetarily.
Mhm.
You have a flow of money, you have people paying each other, and kind of incentives around that. And how do you, whatever you come up with has to not only technically work, like these two entities can talk to each other, but monetarily has to make sense, where there's a way to handle billing and a way that to incentivize both sides to kind of participate if you want your idea to actually be adopted.
That's something I've always really liked about networking research that I've seen. It's like the incentivized actors, like economic aspects.
Yeah.
What do you think are like the three best ideas networking has ever had? Like if you had to summarize the contributions of the entire field.
Very clearly, one of the probably most brilliant things, we have a concrete artifact that is, if you ask a networking person, they'll tell you, I will tell you, it's like the greatest invention of mankind, which is like we have a global internet. Right. Like the fact
I don't think many people would fight you on this.
I think it's kind of an invention on the scale of the printing press, or I don't know, other breakthroughs that we have CRISPR, and we'll see where, like, in biology, it is on that scale, and the like advancement of the exchange of information that enables is just huge. Radio and television, the internet is that big of a thing. So what is really cool about the internet is the architecture that was designed. It's got these layers. It's got these 5 layers. It's got like a application layer, a transport layer, an IP layer, a link layer, and like a physical layer. And that kind of layering design that has scaled from like literally, millions. It started off with carrying kilobytes of traffic, and now it's carrying petabytes of traffic with the same core architecture. The design principles that went into that are certainly one of the most brilliant things that our field has come up with. And that I think we find that applies to other fields as we like these principles of layering and principles of design. This end-to-end principle in networking says that you should kind of build the very core components of your network to do the bare minimum and push any more advanced functionality to the edges. Like build a very small set of primitives that you then can recombine at the edges to do what you need to do. I think these are ideas that are used in other parts of systems. I don't know much about like RISC or whatever, computer architecture, but I think that the similar ideas are there, like build a core minimal set of primitives. But like combining that to build a real world system that's scaled to 7 billion people, that is certainly our greatest contribution.
It's pretty convincing.
Yeah.
Also, that is what transformers are. It's just an MLP, an attention block, an ArrayLu. Well, not really ArrayLu, but and it's just this many, many thousands of times over. Just scales really well.
Yeah. That actually is, in a lot of places, the name of the game. It's like, how do you build systems that scale? It's part of what I love about just being a systems person is reasoning about that scaling behavior.
Yeah. No, thinking of scale is pretty fun. Not as fun running experiments. That's a little bit more tough.
Yeah, certainly in academia.
Yeah. But so I heard that this paper got rejected, and then you took a different approach, got it accepted. How'd the rejection feel? And then also, how'd you pivot?
The rejection felt really bad. I think also, so ML papers, you publish like a lot. ML people publish a lot. And so in systems, it's really tough. Projects take on the order of like a year to a year and a half to 2 years or more.
Oh, yeah.
Right.
I was part of the big systems projects. It's not as fast.
And so it's really painful when you've like poured a year and a half of your life into some idea, and then you see it kind of torn apart by reviewers. I think I learned a lot from that process. I mean, I worked really hard on a paper, and I thought I thought that I could get something accepted out of it, and then seeing that rejection was really hard. But I think in that process, I learned what not to do. And this is my first time writing kind of a legitimate paper. One thing was learning to think about use of figures and effective use of figures.
Yes!
Yeah. So important.
So greedy.
Yeah. And there's multiple sides to it. There's one side of like, okay, how do you design figures that are intuitive? And actually, I think it all ties back to the same thing. Your figure should say something. There should be a statement that your figure is making.
Right.
I think at that point, I was still learning how to kind of run cool experiments and like whatever, some interesting results. Oh, this is how this thing will scale. No, the important thing is there should be a reason. There's a concrete takeaway that, one, a concrete intended takeaway from each figure. And two, that takeaway should jump out right away. And so you should structure your figures accordingly. Like if my goal is to point out that this thing scales like really well, I should show like a thing that scales poorly, and I should show my system and show that the one line is going way up while the other line stays really flat. And someone sees that and instantly that's their takeaway. And that applies to kind of all figures. That was one thing I did wrong that first time around. I think another thing is like, as you go to evaluate your system, one of the things that you should be thinking about, especially as you write your evaluation, is what line of reasoning are you kind of walking the reader through? And think about, so they've just read your paper, the design of your system. What are the questions that they're going to have? And your reader will kind of begin to build trust in you if the questions that they came up with, like that's kind of what you lead with. Of like, okay, well, now that you've seen this, you might be thinking these particular questions, and those are what I'm going to address. I think the way I approached it didn't have as much in mind walking the readers through a particular line of reasoning and having each next question be the thing that I would expect my readers to be thinking next. I kind of wasn't super organized and tossed together all these different bits of evaluation of my system that the readers then didn't really understand and follow and take away. I should have been much more focused on how my readers were going to think. Maybe the last thing is, though, you have to start writing really early. You need room to iterate, and especially important to this whole point about readers, I wrote kind of in a vacuum in the month leading up to my deadline. My second time around went way better when I started 3 months before, and in the couple weeks leading up to the deadline, I had concrete drafts that I could show people, and their questions really informed my understanding of how my reader was going to understand what I wrote. And I think that was the key difference between getting a paper accepted and rejected, was being done a few weeks earlier and having other people involved in that process where I could see how they were interpreting what I wrote. Mm-hmm. Yeah, just some learnings.
Yeah, definitely. I'm in my third year. I learned this every single paper is your writing is like 80% of it. Like you should be spending however much time you think you should be allocating towards writing and experiments, you should be doubling writing. Like your writing matters so much more. Like having a coherent story, even just like I will often run many experiments, and then as I'm writing, I'm like, this actually doesn't matter. Like people won't care that much about this experiment. Yeah. What I should have run was this experiment, and now I don't have time. But yeah, no, it's definitely figures. Figures are big. Yeah. Yeah. People like a visual.
And I think I understand why we end up falling into that mindset, because when you come to like a meeting with your advisor, like you want to have results to show them. You want to run some experiments or something. And so that's kind of the structure that we end up going on. But I've been slowly learning that I think the earlier I can get a sense of the outline and the actual results that are going to make particular statements in my chain of reasoning, I think that's better to focus on than just generating results in general and trying things. But again, second year, still learning.
Right.
Yeah.
I definitely try and write very early now. My first paper I wrote when I was at Microsoft, my first paper I submitted, and it was absolutely brutally rejected. Straight 1 out of 5 across the board. Just eviscerated. And one of my takeaways from that was definitely like focus a lot on writing, like have a story early. Try to kind of like lazily evaluate some of the experimental parts like as needed. Don't run experiments that don't fit into the story.
Don't iterate on the method 2 days before the deadline. That's probably a good idea.
The idea of having a finished version weeks before the deadline, though, I feel like of course is great if you have it, but is very hard to actually do.
Yeah.
It's super hard to do, but I will say one of the other things I've learned in grad school is find mentors that you can kind of look up to, or like look at your peers, look at who you respect and admire. And there's a few people at Berkeley that I've kind of seen their work and respected and admired and have asked about this. And that has been the common thread I've gotten from the people that I see consistently just being able to get papers in, is like they finish their papers early
Wow.
and they get time to iterate. And so it is really hard. It seems like that's like as I think about what I'm trying to develop now, that's like one of the core things I'm trying to figure out how to do is how do I get myself to finish early?
I
Yeah.
don't think I know anyone who finishes early.
Yeah.
I know
don't
people who start writing early, but like have a finished draft like weeks ahead.
So this is like, this particularly came out of my conversation with one of Verluca's students, Emma.
Yeah.
Who's just graduating
Dear
now.
Emma. Yeah.
And she's fantastic. She's just
amazing.
and this was one of her big, like I kind of asked her to walk me through the timeline of her projects.
Mhm.
And one of the things that I think is, from her words, that has made her project so successful is she starts writing early and kind of writes section by section and then kind of iterates with different people on those sections and is done a couple of weeks before. I've asked Sylvia the same thing, my advisor, who was a PhD student here back in the early 2000s. And she also said, hey, like, she told me that, which was tough to hear, but she said she didn't have a single paper rejected during her entire PhD.
Wow.
Every single paper got in. And then naturally my question was like, what's the magic here? How do you do this? And her answer was she finished the papers ahead of time and then kind of had time to iterate.
Mhm.
Because I think the pattern that I see people do, again, I can't really speak to this authoritatively yet because I'm not this experienced senior grad student, but a loose observation is people will like push the last week and pull all-nighters, and then they'll submit the paper and they'll like stop thinking about it for weeks or months until they get the reviews back, and then kind of rinse and repeat. And it feels like that doesn't work as well. It feels like you could stretch that out into more time earlier. Again, much easier said than done, but it feels like the wrong way to kind of go about these like super sprinty, trying to do all you can in the last 2 weeks versus stretching out that writing.
Yeah. No, I think it's certainly hard to do. I mean, I certainly don't succeed at this, but I think like a big thing that I struggle with, and I think a lot of people struggle with, is like, oh, I'm meeting with my advisor, like I need to have results this week and I'm going to spend all my time getting results. When I find that those meetings are usually not as productive as you think they would be, because it's like, these are the results, this is the problem, and this is the solution. And like maybe 7 out of 10 times, they're going to be like, that is correct, go do that. And then like a few weeks before the deadline, this just happened. Like I'm writing this, intro and whatever, and I realize me and my advisors have a different story. Like a totally different story. And I'm like, oh, we are not on the same page. Like we're in the same ballpark, but like what you like, I don't super think that like the way that you're phrasing it is right, but I understand why you don't think the way I'm phrasing it is right. And like it would have been nice if we had gone on the same page like many, many weeks ago.
I have also had that experience. And that's always interesting, whether to like how much to push back versus how much to adopt their view of the work. Because that is, I mean, what a professor is good for. They're certainly not good for like running experiments or not doing any of that. They have an understanding of the field and a certain vision and they, I think, like, how are truffles found? It's like truffle hounds, right?
Pigs.
Truffle pigs. Not to call my advisors pigs. But they have like the same way that they have like a nose for being able to track down problems that are going to resonate with the community that they know. And so then I feel like when I see my advisors kind of forming a particular narrative, on one hand, I kind of want to adopt the direction that they see because they kind of see that as exciting. But on the other hand, I'm trying to develop my own kind of ownership of a space. And sometimes they don't know my particular kind of direction that I've explored. They've just kind of heard some of the numbers that I brought back to them, some of my arguments. And so I found that when that happens, I found it tricky to navigate. How much do I adopt their direction versus how much do I can try to advocate for my direction?
I definitely, I don't know. So I often think that like, I guess ML is so fast paced that there are often times where I am pretty confident in being strong in like, I actually think that this is like a useful direction and that like
Yeah.
people will be interested in this. And I've had some advisors in the past somewhat push back on this.
Yeah.
And I feel like I've been proven right enough times to where I'm like, I think I can agree. What
Yeah.
I'm very bad at is I will often have a line of reasoning or, you know, like a metric or something
Yeah.
that will make sense in my mind, but it, like you show it to one person and they're like, there are so many holes in this.
Yeah.
And I think it's hard to find those holes when you have, you know, 5 other students who are submitting to the same deadline
Yeah,
and you all
for
you
sure.
see them all a week before.
Yeah, for sure.
Which I think it would, should definitely rate sooner.
This is yet another argument. Is
Right.
like you can also kind of time shift, you know, during congested periods for your professor.
Yeah,
If you
exactly.
can like shift earlier.
Yeah.
Yeah.
So what is so you're co-advised, right, by Scott and Sylvia.
Mhm.
Do you meet with them together, like 3 of you typically, or separately?
This varies so much by different student. I find myself working more closely with Sylvia my first 2 years, but now starting to work on projects with Scott and Sylvia as well. I think in my group, people kind of either align a little bit more with Sylvia or a little bit more with Scott in their research tastes.
Mhm.
Sylvia kind of likes to grab problems that are very active in industry now. Well, she grabs all sorts of problems. Sylvia's like a problem mercenary. Like she can go and kind of come in and grab any sort of problem. Scott is fascinated by ecosystem problems. And like you have this entire ecosystem and how do you evolve the ecosystem forward? How do you get all these different actors, both economically and technically, kind of able to evolve to the next stage? This is also his like startup Nicira that he sold to VMware or Cisco, I forget who bought it. Anyway, it was kind of all about this: is how can you get people to adopt SDN? And so he gets this very kind of high level perspective on things and view of kind of how these ecosystems evolve. Sylvia kind of works up and down the stack in the middle. So she kind of likes to think systems for a particular system and likes to get into the details also. And so I'm finding that certain projects kind of fit. Some projects fit Sylvia's taste better and other projects fit Scott's taste better. So right now I meet with Sylvia every week and multiple times a week. And with Scott, we meet every 2 weeks for a particular project that we work on. And it's a bit of a more separate advising style. You know, I know other people in our research group meet every week with Scott and Sylvia in a single room.
Oh, really?
Yeah. Though I do find in our group that all of our meetings, we don't have like, you know, our meetings seem to be much more around projects, particular projects. There's a project meeting, and that's where you see your advisor. I don't know. You're also co-advised, right?
Yeah.
How does it work for you?
I think pretty much all my meetings are separate. The only time I meet like with all of my advisors together is like right before a deadline, and even then it's not like we meet all together maybe twice before a deadline. This tends to work pretty well. I remember trying joint meetings and it just didn't really work. It's not that it was unproductive. It's honestly more of a scheduling thing. Like it was like about as productive as if I had 2 separate meetings, but it was like 3 times as hard to schedule. So it was like not really worth it. I think I feel like with systems projects, there are certainly, I feel like meetings are much more project centric than they are person centric.
Yeah.
Like I think most of my meetings now, I guess now I'm part of a larger project and those have a lot of individual meetings, but like I think now I have like just pure individual meetings, which are both a blessing and a curse.
Yeah. One thing that's nice about the individual meeting situation is that, for one, it's definitely possible to have too many cooks in the kitchen.
Oh, yeah.
And professors have ideas. They have lots of ideas. They'll share ideas. They'll share directions. If you get a couple of really opinionated professors together, they can go off in professor land and do their thing. And that can be tough. And the other thing is like having someone that feels kind of responsible for your project is also important. And so kind of I've seen projects and been part of projects where there's multiple professors involved and then they can kind of all disengage potentially. Or when you're working one-on-one with a particular professor, I think it's easier to stay focused on their vision and your vision together rather than trying to navigate multiple people's visions.
Yeah.
Yeah.
I agree.
Yeah, I don't know. What's your experience like, Connor?
Yeah, and so I'm solo advised. I've had various projects. There's been like a recurring project meeting of, like maybe a couple of professors and some grad students, undergrads. I've never found that format that productive. I definitely prefer like defaulting to not meeting in that sort of setting, and
Yeah.
only meeting if there's like real content to talk about.
Yeah.
And I've had some projects where I've had like external collaborators. I've met with like, me and two professors, and I find one-on-one meetings like much higher bandwidth for me. Like, the situation where like two professors like run off in some direction on their own, and then you have to like pull it back to like the direction you want to take it in. I find like too randomizing kind of.
Yeah.
Easier to manage just one-on-one.
Yeah.
So what does an advising meeting look like for you usually? Like, are you like preparing a PowerPoint to go through? Or you're like making graphs and running experiments? You're walking with like questions you want mentorship on, or like
This is something I'm still working on improving. My meetings are fairly unstructured. I've tried meetings where I have like slide decks. I end up making kind of an agenda the day before or the morning of what I want to walk through. And so during the past week, I've kind of worked in different directions. I have some results, and I have some structure that I want to like, some argument that I'm trying to chase down.
Mm-hmm.
And I end up wanting to run that argument by my advisors and see if they buy it, and also share the results with them and see if they're as excited about them as I am, or they see the kind of takeaways in the same way.
Yeah.
I know that some people have much more, like they have a slide deck, they update the slides each time they present the slides. My meetings don't end up going like that. I think I have a more, my advisor is very engaged. Sylvia's super engaged in the details of the projects that I'm working on. And so I don't feel the need to do that as strongly. One thing I've heard that people do that I want to try is kind of preparing 24 hours in advance, like an outline and notes and stuff, and sending that out. And that seems like a really efficient way to run meetings and avoid wasting time.
Yeah.
Avoid filling time. One thing I've struggled with is there have been times where I felt like I'm meeting too frequently with my advisor.
Yeah.
Well, because I do find that you don't always have some weeks
you just don't have anything.
You just don't have anything.
Yeah.
That's part of the process of research, I think. And actually the worst thing, I find that the worst weeks are when I feel like I don't have anything a day or two before, and I like scramble to get something. But that scrambling often is not kind of deeply thought out. It's more like, what's the thing that'll get me results that I can talk about?
Yeah.
And so that's one thing I'm trying to improve on is I've actually liked my new project now has meetings every 2 weeks, and that's kind of nice because it gives me room to kind of come up with, think more process oriented, kind of figure out what argument I want to make and explore before the next meeting. That's the thing, by the way. Before grad school, I asked people how much they met with their advisors, and at different schools where I got admitted, and hearing some schools where you only meet with your advisor half an hour every 2 weeks or something, I was like, God, that's nowhere near enough. You can get a lot out of professor time, and actually, it's not that you want to meet with your advisor multiple times a week necessarily. Like, there is such thing as too much.
Yeah. No, I'm pretty strong in I think you want access to your advisor, like once a week, maybe even like 2-3 times a week, where access is just like you have 5 minutes where you can run something.
Yes.
But in terms of like dedicated meeting time, 30 minutes, an hour every 2 weeks, it's like usually not too bad. Especially, I mean, not if you're maybe a first year, but
yeah. That's a great way of thinking about access. I hadn't quite thought about phrasing it that way, but that's exactly it. And that's exactly what I value about my advisors, and what I hear people complaining is like when their advisor is so checked out, they can't kind of come in and they never see them.
Yeah. I think it's nice because like my advisors have like everyone goes through periods where they're more busy or less busy.
Yeah.
And I think in periods where they are more busy and they aren't accessible like they're only accessible through our like weekly 30-minute meeting.
Yeah.
I get like a lot of stress of like, oh my gosh, I need to present so many things in this meeting. I need to remember like all the things because I won't have access to this person for another week.
Yeah.
And I think that ends up just almost resulting in like more wasted time because I'm trying to just like blabber out every single result, and then we don't really have time to discuss the results. And then whereas like oftentimes I'll just be like, oh, I'm thinking of running this experiment, and they're like, oh, that actually sounds wrong. I'm like, you're correct, actually. You saved me so much time. Oh, I want to prove this hypothesis. Oh no, that doesn't, no one cares. Oh, that's correct. Wow, thank you.
Yeah.
They'll say it nicer.
Yeah.
So how has being part-time at Google during your PhD kind of changed the PhD experience? Does it influence your research? Do you end up allocating a lot of time to that you feel like you wish you could have spent on research? Like, what's the deal?
Yeah, it's tricky. I came into it thinking, hey, this is like the ideal setup. I hear people say that a lot when I like mention it. Working part-time here, doing research in my fields for industry. But it certainly has clamps down. Certainly the first year and a half of my PhD was spent doing a lot for it has affected kind of the problems that I decided to work on early on in my PhD. And so I think there's pros and cons. It's really nice being able to justify my work with real world systems. It's also been really nice even just absorbing like a sponge all of the things I see inside of Google, the outages that happen, the trends of where things are headed. I think I have a good taste for what matters in the real world, which is important in motivating systems papers. At the same time, it seems like grad school is an important time to kind of walk around and explore new things. And having my taste kind of restricted to the subset of things that right now are the flavor. It's more than just the flavor of the day. ML is not just a flavor of the day. It's clearly here to stay. But that's what I see my focus put on potentially. That's what Google's focus is really on. And so that's a bit of a trade-off. Like there's another PhD student in my group that's working on like building networks for like collecting data from climate sensors and on volcanoes or something. Like I have not been as free to explore those directions. It's not, again, I'm only part-time at Google. It's because my head is in that space so much that even outside of that work,
it's just hard to context switch.
Yes, the context switching also. Yeah, totally. It's much harder to make progress when you're switching. So yeah, it's interesting. It has trade-offs. I think people come and ask me, people in industry that want to come back to grad school ask, hey, should I do this? Should I try to work part-time? I generally would actually advise against it. I think it feels like grad school is a good time to kind of come in and just focus on learning both about yourself and about the field. But it's different for each person. They have their own reasons for needing to work or wanting to work.
So is your research you publish in grad school using like Google data sets and like on problems related to Google, or is it purely open data that you are inspired to work on?
Any Berkeley research is kind of can't use Google data for. I have a very concrete kind of area that Google timeout and still working on, which is kind of wide area network routing, that decentralized software-defined networking thing I was talking about. And then my research at Berkeley is completely separate, which right now is like bandwidth allocation for self-driving cars, like how self-driving cars should share.
Wow, back to AI.
I know, always. And so, I intentionally try to keep that also very separate because I can't kind of dip.
So the paper that's going to be at SIGCOMM is like a Google-y paper.
It is a Google-y paper. Yeah.
How was the transition from industry to research in terms of like, how'd you get into a PhD?
Yeah, that's fun. I like failed at research as an undergrad, like didn't really get anywhere. And went and worked at YouTube for 2 years and then did some teaching that I mentioned at Howard. But I started working part-time in a research group at Google, in the systems research group, doing networking research. I just got really lucky with who was there. Like David Culler had just come to Google and along with Hank Levy started this research systems research group, and they had hired in as one of their first hires Sylvia. She came for a year on her sabbatical. And I reached out and I just offered, hey, I don't know about research. I'm not any good at research yet, but I do know how to build things at Google. And again, the situation was you have these pretty famous, important professors that have gotten together inside of Google, but they don't know how to build things, right?
Like that's you not found the need.
They are used to having kind of grad students or whoever kind of doing the building and running experiments. And so I found kind of this exchange where I had experience with Google tools. Sylvia, kind of obviously an incredible world-class researcher, and I got to learn a lot from her. And after kind of part-time, just in my evenings running experiments for that group, they had an opening and I transferred in. And yeah, I worked in that group for about a year before I went to grad school. I got my letters from that group. I got my letters from a professor I TA'd for, actually Scott Schenker, who is now my other advisor, from Sylvia, who I done research with at Google, and from my manager on my product team, who just basically said, yeah, Alex was a good engineer and worked well with his teammates.
Not Alyosha?
Not, well...
Alyosha's rec letters they're as dramatic as Alyosha is.
Wow. I think it might have been dramatically bad for me because my project did not go well. As much as I tried. And so, yeah, I ended up applying and got into a few schools and chose to come back to Berkeley, which was very full circle for me because I TA'd for Scott. I'd worked with Sylvia at Google.
Yeah.
And it just worked out well.
Wow. Yeah. So would your advice for people who are in industry and want to go into academia luck out or find professors who need grad students?
Okay, so the advice there's a couple of pieces of advice. Working backwards from graduate admissions. In grad admissions, turns out that the thing that matters most is your letter of recommendation. And the other thing that's surprising is you don't need to have published, I don't know how to phrase this because it's not a universal. What I was worried about when I was applying was or even trying to get started was I'm going to need to publish papers to have any chance of getting into grad school. The letter of rec, you need someone that can vouch for you and say this person is someone that has the potential or can do research. Yeah. And really, oftentimes that boils down to being kind of reliable and being able to figure things out kind of on the fly, and just being a good person to work with. And my letters, I didn't have a paper yet when I applied. I hadn't published any papers, and I got into all these good schools. It was way more about having a letter that said, I think this person has potential from someone that's part of the community. Yeah. So those are the two pieces. You could have a fantastic letter from your software engineering manager that says, wow, I think super highly of so-and-so, and you should really take them to their program. They're the best person I've ever worked with. But it needs to be also someone that's kind of in the community in some way. And so working backwards from that, you should be looking for research opportunities with someone who's in the field who can write your letter. I'll also point out a lot of labs, especially large labs, you don't get to work with the professor, especially if you have no experience whatsoever. You often work with a grad student or a postdoc. And those are okay too as well, because what happens is the grad student or the postdoc writes the letter, and the professor kind of either quotes from that letter or takes that letter verbatim and mostly wraps it and signs it. And that can work out well too. Working backwards from that, then look at the skills that you have and what you can offer, what you can bring to the table. Especially at a large company, you have kind of a knowledge of how to build and how to operate. Within Google, there's all these different tools, and having that knowledge, you already bring something of value to the table, which was a key thing for me to that was the key observation that I think let me join this group that otherwise I would have no business being a part of.
Yeah.
It was there are all these fantastic researchers, but it takes, a year to learn your way around the tools and development processes. And so that was really useful for me at a big company. If you're at a big company, seek out, offer to work kind of in your spare time, 20% time, whatever. If you're at a smaller company, I think it's trickier. I've seen other people be successful by finding research opportunities at a university nearby and offering to work. But again, lean into some skill that you have, which is if you're a software engineer, a few years into your career, you know how to build things, you know how to code, and that's something you can offer. You can build things, you can run experiments. I think that's kind of the in to getting a letter of rec, which is what you need then to get into grad school.
Yeah. Agree heavily.
Yeah.
So that's how you'd advise that someone gets into grad school.
Yeah.
Would you advise that someone goes to grad school?
Oh, this is great. This is great. I've written drafts for myself of these 2 blog posts. One is why you should go to grad school, and another is why you shouldn't go to grad school.
Yeah.
Really important. Okay, this is great. I'll dry run my ideas here.
Yeah.
One important thing is one reason not to go to grad school is some people think that, okay, I really loved undergrad, and then it ended, and I'm back and I'm just going to go back to school. I loved being on campus. I loved always learning and taking classes. That is not at all what grad school is like.
Yeah.
And it's really funny, actually, like here being a grad student. I'm even at the same school, but the experience is totally different, different experience. So don't go back because you think that you just want more schooling. Another bad reason to go is just like, I'm lost and I'm disenchanted with working at my company. And so I'm just going to take a huge pivot and I'm going to go try to go to grad school. Maybe with that approach, it'll even be hard to get into grad school because just this kind of I'm lost and I want to go do something else isn't a great reason to kind of make that pivot. It's a good reason to start exploring and questioning what you're looking for. And if that lines up with grad school, then that's a good next step. But just the jump from I'm bored and I'm going to go to grad school won't cut it. I think good reasons to go to grad school are, for me, compared to software engineering. In software engineering, especially product engineering, the incentives are structured such that you have a feature you need to build, and you want to get that feature out the door as quickly as possible because you want to maximize the number of features you're building. You want to maximize the number of users that are seeing your features. And so I felt like the incentives were such that I would learn the minimum I needed to do to get the feature out. And, I'd copy and paste code where I needed to, or I would go and use whatever framework that the system was already, whatever the minimal amount of work I needed to do. And I had this yearning for deeply understanding my system inside and out, and why it works the way it works. And that was not at all aligned with product engineering. And so maybe that's one thing, is if you're just really curious about what makes these systems tick and how they work, that feels like a good idea for why you might want to go to an environment where the incentives are more aligned with understand this thing as deeply as possible and see what insightful new ways you can kind of approach it with. Other reasons to go to grad school. Obviously, okay, if you want to make like money and just like live the most lavish life, or like you want to go skiing every weekend, grad school, not good for that. Though plenty of grad students do still go skiing at Berkeley, go up to Tahoe. Maybe another thing is like, okay, this is the other big thing for me. I have found that a good reason to go to grad school is to like learn to sharpen your thinking or to clarify how you think. It's one of the like most incredible things seeing my advisors, the way that they break down a really ambiguous space and like structure an argument. That's a really big thing that I felt like wasn't valued and wasn't used that much in industry, oddly enough. And it was one of the things I wanted to get out of grad school, was being able to think that way. I don't know. Do you guys have others? What are reasons to go?
Well, I think the purpose of grad school is learning how to fail in a controlled environment. So I think, I don't really know if I would say this is like, I don't really think anyone would want this, but like, I think the potential upward mobility for grad school is like very high. Like if you hit it big or if you do well, you can do very well, and you can you have a lot of freedom to do what you want. My experience, I know there are other people who would disagree with this. I think you can really like make your way into spaces that you want to be in if you try hard enough. And I think in industry, that upward mobility is maybe not as like, you might not be able to get exactly where you want to go as fast, but there's also downward mobility. Like you can fall far in terms of like, you could be failing at everything. You could feel like you've wasted multiple years. You now have no money. So it's if people really like that, like, I really like being uncomfortable and learning how to like sit and be uncomfortable and like how to get myself out of that. I also, honestly, if you want to do a startup, grad school is not a bad idea. Like, it's a good way to learn how to make ideas. You have to learn how to market the ideas. Like, you have to learn how to deal with failure. If you can try mentoring undergrads, you learn how to be a manager. I mean, you're learning all the same skills.
It's interesting you say that. I would push back or question on I feel like in startup land, you can also really quickly make your way into new spaces. Like I agree with you for big tech. I agree with if you go to Google or Facebook or Meta or Microsoft or whatever. But it feels like in startups, you can pick a domain and pretty quickly with kind of raise some funding and
this like upward mobility.
The upward mobility thing.
I agree. Startups, I think, have a similar. I mean, I guess I've never been like actively trying to do a startup, but I could agree that I could believe that startup has a very similar thing. But yeah, I guess it's two sides of a coin. Startups, I mean, I guess you start off making no money unless you've started getting funding. So
yeah.
Grad school just might be a ever so slightly more economically stable startup. Reasons not to go to grad school is definitely like, if you really love school, definitely don't. If you trying to think of any other good ones. I mean, I guess if you really want to seem smart, I think this is why I went into research, and luckily it was fine. But like, if you really want to seem smart and you feel like people perceive you as smart, like you lose that so quick. At least I did. Like, it immediately dissipates and you realize you are not very smart, and it really rocks a lot of that.
Yeah, that's definitely true.
Yeah, people who are like, oh yeah, my parents went to grad school. Absolutely not. Don't fall into that. People who think that I will make a ton of money after I leave grad school. I'm not necessarily arguing that you won't.
Yeah.
You probably will.
Yeah.
But if you are in tech, you're probably going to be making a lot of money either way. So I don't really think that like monetarily this will be a net positive.
Yeah.
Or enough of a net positive to matter.
Yeah.
I think it's actually, I think people who, like, I guess grad school is quite naturally for people who like maybe don't like like a 9 to 5, or they don't want to be like told what to do. I kind of push back on that. Like, I'm sure grad school is great for them, but like I was definitely someone who like, I love a 9 to 5. Like, you give me a task list, amazing. Like I love that, like well-defined. I would be an amazing software engineer at Google. Like I really enjoy that, but get like this like pushing yourself out of your comfort zone. Like I think that really unlocked a lot of stuff for me of, oh, this is actually also quite fun. But I don't think I'd give that as advice to people. I don't know. What about you, Connor?
So like the people in grad school, I think, are really like good. Like people are very motivated and very bright, and like it's like a pretty unique environment in that way.
Yeah.
I don't know if that's something you're looking for. I think that it is pretty rare environment in that way. Just like, how like jazzed people are about what they're working on. I think it's hard to find.
So would you say people who you would not necessarily recommend grad school for people who say they're in industry, they're very unhappy with their work, they don't find much joy in it, but you would recommend grad school to people who are maybe fine with their work, but they really aren't happy, but aren't satisfied with like the interactions that they have with people, in terms of like they think that people are more checked out or aren't as passionate about. So like more they're unhappy with the environment.
Yeah, I guess.
Well, I guess.
And if they're passionate about research, like if you go to grad school and you don't like research, and everyone around you is excited about research, probably it's not tough. That great of an experience socially either. But
I think you can get that. To me, I hear people who go through that at like a big tech company and then switch to a startup where everyone's jazzed about a particular problem. It'll be like, whatever, building like the dashboard for insurance for like selling, I don't know what, like boats or something. But you end up finding people that have a passion around the same area there too.
Yeah.
What do you think is different in the grad school environment?
Well, I've never worked at a startup. It might be exactly the same. I don't know.
Mm.
Have you ever worked at a startup?
I haven't. I just
I have, and I don't know.
Oh, there we go.
I mean, I would not say that this is incredibly common, but maybe I just haven't worked at the right. I mean, this happened it does happen, but I don't think it's nearly as, similar as grad school or anything. Yeah. I do think a good differentiator because I do think it's hard for people to like suss out, do I want to go to grad school because I like the idea of a PhD versus do I want to go to grad school because I like research?
Yeah.
And maybe they've already done some research.
Yeah.
It's like, if you find yourself really wanting to talk to people about like the high level ideas or it could be your project. At least from undergrads, I've seen that this tends to correlate a lot with how much you like grad school. So there are undergrads that are like pretty good at research, but they really only like, they talk about it with their advisor, they talk about it with their grad student. And then there are students who like, go and seek out people to talk to, and they'll go to these talks and they'll like talk with the speaker afterwards about their idea.
Mm-hmm.
I think that seems to be a good indicator of you probably like this.
Mm-hmm.
Or I guess you could be really shy and not, yeah. And then that would be a great indicator, but
yeah.
I don't know.
I think if you're very wealthy and like it might just be like a fun thing to do for a while.
Yes. Oh my gosh. If you're like, your kids are out of the house and you just want a way to pass the time, I'm so pro, like you should get a PhD. 100%.
Retirement PhD.
Right. Yeah.
Your mom did this, right?
Yeah. This is why I have this thought.
In what?
Kinesiology. She's a physical therapist.
Wow. That's cool.
Yeah. And ever since then, I'm like, my worldview has changed. I mean, granted, not that easy to get into grad school if you've been out of school for 20 years. But if you can do it, oh my God. Like, it sounds amazing. At least the way that my mom describes it, like, stakes incredibly low. What's the worst that's going to happen?
Yeah.
If it's in a field you're already interested in, like you've, worked in for your whole life.
Yeah.
It's like, the space pretty well. Yeah. The needs, like, and usually, like, hopefully you're, financially stable at that point.
Yeah.
Hopefully you're a bit more like established in yourself at that point.
Yeah. I feel like in general, like a lot of the hardest parts of grad school are like the pressure that grad students put on themselves.
Yeah, for sure.
Like if you're not aiming to get a certain job after grad school and you're just kind of doing it for fun, then probably a pretty good time for a lot of people.
Yeah. Well, thank you so much. Any parting words for prospective grad students, current grad students?
So yeah, actually, one of the really hard things shifting into research from being not at all in research was learning to read papers. Maybe my only parting word was I wish someone had told me this early on, was that like, I think it's hard for everyone when you start reading papers. Like, it's difficult to start to learn to absorb, especially because it's a new field and there's papers kind of assume you have knowledge about other things. They have citations and that's great, but they're also just ideas that are sprinkled through that are known to the people in the community that are not known to you. And so don't let that discourage you if you do start. I just remember when I started reading papers in the beginning, I had some doubts because I was like, man, this isn't really all clicking for me, or these are really hard to read, or it's taking me so many hours to read one paper. But that's like normal. And it's the sort of thing where if you just exercise that muscle, you will kind of absorb that space and be able to start to read papers much more easily. So I only share that because I remember that being a tough thing for me. And I didn't have anyone to tell me that when I first started reading these papers.
Yeah.
Like it does get better. But otherwise, yeah, it was a really fun conversation. Thank you.
Yeah, thanks
of
for coming
course.
on.